So thank you very much for that invitation, Michael. I'm quite excited to be part of this, and it's a great reason to come together to celebrate the work that Marcy has been done for decades. And I mean, I'm not in laboratory education, but Marcy, you were always present on conferences, and I'm always we're looking up to you, to your work. So I'm excited that I can be part to celebrate this today. As Michael said, we have started to look into the whole area of machine learning and using that in chemistry education research. So we'll take you today onto that journey that we undertook like a year and a half ago. But I also have to say that I'm not the expert in that field. I have incredible people that have taken that endeavor of using machine learning in their research. Foremost, Paul is a great doctoral student in my group, and he collaborates with Brandon, who is a postdoc in Jeff Racker's group, who was a doctoral student with Jeff. Now he's with Marilyn Staines at the University of Virginia. And we also collaborate with Professor Peter Wolf. He's a physics education professor in Germany. So what I will do today is I will give you a brief overview about some basics of machine learning so that you know the terms a little bit, that you have a good understanding of what that is. Then I will tell you a bit what our educational goal was that led me to start ML in chemistry education research, and then what we use as a foundation to work together with the machine to actually analyze students' reasoning. So maybe you have heard of, about some terms that are used in machine learning. So machine learning is actually kind of like a subfield of artificial intelligence that focused on the development of algorithm that can learn from data and make decisions with kind of minimal human intervention. So kind of we can use machine learning models to do the work that we probably would do by hand, but it would take even longer when we would do that. So we have unsupervised and supervised machine learning techniques. Both work with all kinds of data. Unsupervised machine learning is characterized by a process where you just put unlabeled data into the algorithm, into the machine, and then the machine can detect certain clusters or groups. So this is kind of more like a typical clustering technique. On the other hand, supervised machine learning models work with labeled data. This could be, for example, student answers to open-ended tasks. That could be interview sections of students, of learners. And then your labeled data is used to train the machine so that the machine can then categorize unlabeled data or new data in the future. So kind of the machine learning model is learning to find the categories that you put in. Another term that is also used quite often is large language models. This is what ChatGPT is using. And large language models are a type of deep neural networks. This is comparable to the human brain. We have different neurons, and information or language is sent through the deep neural network. And these algorithms can then calculate contextualized embeddings. This means that they can understand what is the surrounding of a word, what are typical words that often appear together. And for example, a large language model that is often used is BERT. So this is easy to remember. And BERT can capture the context-dependent meaning of individual words and also the dynamic relationships. What I mean with words in relation, I'll have a funny example for that. And this also shows how transformative deep neural networks or machine learning could be, is that these algorithms are actually capable of detecting subtle meaning differences in sentences. For example, if I would give you that sentence, this has a certain meaning, but just by changing slightly the place of the word that is highlighted here, So this changed the meaning, and I'm not changing the words here. I'm just changing the place of that word, but I can continue doing that. And so a large language model is capable of detecting the differences between these different sentences here. Or I can also place it at the end. So this is just to give you an idea how transformative this is, because you might think, I mean, algorithms can calculate math operations since years, but language has always been a huge problem for algorithms and machine learning techniques. But with the use of these large language models, this is actually capable, and we can use that in chemistry education also to help us work with student texts and written answers that we typically collect in research studies. So what is our educational goal for implementing machine learning? And it was, from my perspective, not that much that we said, I have to find a case to use that method, but rather we have a case in our research and we're hitting a dead end. So we needed to come up with new ideas to do that. So I will illustrate how we did that. A couple of years, or maybe like 2 years ago, Leonie from my group started to look into students' argumentation competencies and were interested in how students are arguing about different reaction pathways in organic reactions. So she created these 4 task sets, and you see the red encircled reactions are more unplausible reaction pathways, and the green ones are more plausible pathways. And we asked students to build arguments for these different proposed reaction pathways. So we did that online and prompted students to rate the plausibility of these reaction product cards, and then gave them the opportunity to build an argument and to write down their arguments in the text box for evidence. And then also we asked them to justify the evidence by reasoning. So we're following the typical claim evidence reasoning model that is commonly used in argumentation and science education research. Then we had to code everything by hand. So we did a typical qualitative content analysis. We had around 1,000 arguments, and we were looking if students were applying concept knowledge in their arguments, if they supported their claim with evidence, and if they justified their evidence with reasoning. And this took Leonie and also a research assistant quite a while. So they were sitting in a seminar room for a week coding these arguments by hand. And as a ChemEd researcher, although I'm quite focused on research, I thought this would never happen in practice. I can't, you know, and even if the results were good from that study, this will not even happen in practice because no one has time to actually spend so much time to code so many arguments in a semester. So I said to myself, we need to make use of other methods to automatize that qualitative content analysis that we did in that study before. So I took again my 1,000 arguments and I hired Paul in my group and said, Paul, can you automatize that? Can you use machine learning to help us be more quicker in analyzing these? And then he went ahead, and maybe 1 month or 2 months later, he came to me and said, yeah, we can do it. We can automatize that. Here we used a supervised machine learning technique. So we had already all our labeled data, and so we could train the machine to detect the data. And with 90% accuracy, we were able to detect these 3 categories that we were looking at for students' argumentation. I said, okay, that was a quick fit to my problem. But then I thought, why not making more use of machine learning? Because maybe there's more behind that maybe there's more than just the 3 codes that we were looking at students' argument. And I wanted to dig deeper and see, can we define other categories, or with the help of the machine, find other subtle differences in students' argumentation. So with this, we came across the computational grounded theory framework. this is kind of a little bit related to what we probably know from qualitative data analysis, the grounded theory. Here, the difference is that you use computational methods to help the process of digging deeper into the data. So this computational grounded theory proceeds in 4 different steps. The first step is more an exploratory step, where you use the machine in an unsupervised way to help you get an idea about what is in the data. And then you have to go back to the literature and the pattern refinement step to actually make sense of that, because the machine is not telling you what to do. It's rather, it gives you clusters and then you have to make sense of them. And then in the third step, you could use your rubrics or your categories to train a machine, so to use supervised machine learning techniques to be able to detect your new categories and new data. And I'll give you some ideas later also on the 4th step, which is the pattern transparency step. These are like tools and ways how to understand how the machine actually works. So kind of to look behind the model to understand and to see why the machine is making certain decisions. So when we started the unsupervised, our cluster analysis at the beginning, we got like a 3-dimensional space where all the different arguments that we had, 1,000 arguments, appeared in a this two-dimensional space, and one dot is one argument. And you can see by the colors that some arguments are more closer to together, and this clustering algorithm looks for similarities and density in terms of the language that is used. So we found around 20 clusters here, and then we were just printing out the clusters that the machine was giving us and set together and tried to make sense of it. And our first inspection of these different clusters gave us some topic categories that we see in students. So students were talking about shards, species, and substrates, nucleophiles, electrophiles, acid and bases. And maybe not surprisingly, thermodynamic and kinetics were also one category by itself. So here we see what we see in the literature as well, that students are not connecting acid and bases and thermodynamic aspects together. This is why it appeared in different categories. But we said this, I mean, this is obvious because all the reaction contexts refer to nucleophiles, electrophiles. And so we continued looking into the literature to see if there are other frameworks out there that could help us to make sense of what we see in the clusters. So as I said, the first category were the topics. So we differentiated between structural and energetic categories. And then we used the modes of reasoning framework from Sevian and Talanka, which kind of describes an increasing sophistication and causality. So from a rather low descriptive mode of reasoning to a higher linear causal mode of reasoning, which we could see in the arguments appearing as well. And then we used from Alison Flynn and Jackie Dang their description of granularity levels. And so we used here the categories phenomenological and electronic. So structural and energetic were already covered by the topics that we had. So we had kind of like a 3-dimensional framework thing that we needed to combine and put onto the 20 clusters that we had. So this kind of looked like that at the end. So all these boxes, like 20 boxes, could be or can be described by different aspects. So by the level of granularity, by the modes of reasoning. And for example, that category here, so P stands for phenomenological. So this argument that a student would give here in that category talks about measurable properties, for example, uses pKa values, but is not that much talking about electron distribution. And descriptive means that that argument is referring to explicit properties of molecules, but is not establishing a cause and effect relationship. So it's rather basic argument. So with this rubric categories, we went back to the data again encoded the entire data set again, these 1,000 arguments. So because we need to label the data so that we can further use a machine learning approach to train the machine to detect these categories. So we need to know which argument falls in which category. So this is now the third step. This is where Paul started to work again around training the machine to detect these different rubric categories. And here comes BERT again. So we also make use of large language models to help to classify the arguments. And you can see that we have like 3,000 arguments, or 2,000 arguments more. So we were collecting additional data from different institutions as well to be more diverse in terms of arguments. And then we could split the data into 3 different sets: a training set, a validation set, and a test set. So this is a typical method that you do in machine learning, so that you split your data in different sets. On the one hand, one that is there to train the model, kind of to help the algorithm learn what to look for, a validation set to determine the hyperparameters. These are epochs, learning rate, and batch size. So you kind of have to calibrate your algorithm to achieve a good classification of your categories. And then the test set, is there for checking the accuracy of the model. With all this procedures, we could arrive at an accuracy of 93%. So with that accuracy, we are able to categorize student arguments in one of these 20 categories. So as I said, I want to talk also a little bit about pattern transparency, or what we also did to kind of check how our model is actually working. So we used, for example, ChatGPT, and asked ChatGPT to build us arguments about the reaction's plausibility. And so we used these arguments and used them to train, to check if the accuracy of our machine learning model would still be in a good range. So this kind of diversifies the model a little bit and helps to check if the model also works with different sorts of data and different ways of how arguments are phrased. Then we also did a black box analysis. So we were taking some arguments and we're changing small like pieces that we added into the argument, and this would require then that the argument is classified in a higher category, so from descriptive to relational. And so we could check if the model is working correctly. So these are different aspects that you can do to understand and to trick the model if it's actually working well. So I haven't talked until now quite a lot on how we are going to implement this. So maybe you have that same question. So what is next? So we have talked about all the technical stuff and you've learned a lot of new terms, but what is next with that machine learning model? As I said, I had the plan to put that into practice, and we actually did that last year. So my vision was to implement that machine learning model over a semester and to longitudinally support students in their argumentation competencies. So we have again our 4 reaction task sets. And every time a student is producing arguments, the machine learning model in the background is analyzing the level or the quality of the argumentation. Then students get an individualized feedback for their arguments. And then also what is highlighted in that colorful bar here, they get adapted exercises. So these exercises refer to their current level of understanding that they show. And so over the semester, students are here supported to based on their individual level of knowledge to build arguments in organic chemistry. So we have a couple of research question around that. And we just collected data in November, so Paul is just very busy in analyzing the data and finding ways of actually describing the learning trajectory of students over these 4 different time points, which is not an easy task. But from our perspective, we are interested in, is that actually working? So what are the competencies that could be improved over time, or at least maintained over time? Or are there some sort of difficulties that decrease students' performance longitudinally over the semester? And also maybe more of that emotional affective side, to what extent do students actually feel supported by such a machine learning based instruction? So these are all the things that we are going to look into in this year. So I'd like to, I'm a bit running out of time, I'd like to summarize a bit what I try to illustrate you today, is that you can use a combination of different machine learning techniques and make use of large language models to be able to detect multiple aspects of students' reasoning. And you can do that longitudinally. And compared to other research studies in the last decade, we could use our machine learning model also with different reaction and task contexts, which was also something that was difficult in earlier days. And we can use the automatized analysis of this rubric to provide students with tailored feedback, and also with scaffolded support or with adapted exercises for their level of understanding. So this whole area of machine learning is quite exciting, and it's also, it has a high pace. So you really have to be on the forefront and read a lot, kind of to dig deeper into the different techniques and methods. And this is why I'm so glad that it's not me that has to read a lot, but Paul is doing the work. So I have to give credit to him and to Brandon and to Peter, who are involved in that project. And whenever you're interested in machine learning and you need a critical friend or support to dig deeper into that, feel free to reach out to us or to consult the references here. And with this, I hope there are plenty of questions. And thank you again, Michael, for inviting me. And thank you all.